The problem at hand requires the designing of a self-sufficient energy system for a property in northern New South Wales. With the limited grid capacity and reliance on rainwater and 4G networks, the site faces significant constraints. In essence, the property has an energy demand of 25.7 kilowatts without EVs and 43.5 kilowatts a day with them. The location also offers high solar potential, but lacks sufficient grid infrastructure. We'll address this by designing a hybrid system which combines solar, wind, and battery storage, thus ensuring sustainability and a reduced dependency on external resources.
What does the client need? Since the clients are striving to live more sustainably, the sustainable energy system must provide long-term energy for the client's house and two large sheds, which are used to power the part-time work on their farm. They also possess two diesel-fueled cars, however, they do wish to acquire electric vehicles once a full range of models are released in Australia. Therefore, the system could include specs to accommodate electric vehicles, whether it be built immediately or built in the future as an add-on to the system. What does the client already have that we can capitalize on? Firstly, the locality of the rural area, which makes our solution highly suitable for wind power. Secondly, the 112 hectares of land, which gives us the freedom in the size of our solution. Lastly, their low to mid six-figure income, which means that they're likely able to invest in a high quality long-term solution.
To now present the design alternatives for the client's project, we have design solution one. This is our bare bones design alternative. So this includes a 10 kilowatt solar PV array as well as a 5 kilowatt wind system. Due to the property's high solar irradiance, the solar array would be the primary renewable energy, with the wind turbine system being a supplement, as there's high winds in the region, but it is intermittent. So this will all be stored in our 30 kilowatt hour battery management system, and this should supply the energy demands calculated from the client's CFP. So this is a non-grid tied solution, so it has a low life cycle costing, but it does have sort of a high environmental benefit. And for design solution two, so this mainly the difference is it incorporates the electric vehicles as well as it being grid tied. So due to the electric vehicles, we have a higher sort of energy demand for the farm. So we've doubled pretty much everything here, where we've got a now 20 kilowatt solar PV system, a 10 kilowatt wind turbine system, and this is all stored in a 50 kilowatt hour battery system. So this should meet most of the energy requirements, but this is grid tied just due to reliability issues. So with EVs, it's quite a more substantial life cycle costing. So you have to have a charging station and everything that's needed there. But if you factor in a 10-year sort of system boundary, you will sort of have a 35 tons of CO2 emissions over that life cycle per vehicle. So we believe this is also to be in line with the client's needs.
Solution 3 has the same electrical system as Solution 1 that should power the house and their needs but not power EVs, as we will be currently using the client's current diesel-powered cars, which produce this much carbon each year. If we plant 10 hectares at least of trees, which is the amount required for a try to do it for free, that'll comfortably cover the emissions of the cars, and indeed, given the amount of carbon absorbed by trees, particularly when they're younger in the rapid growth phase as they're establishing in a new forest, it should be able to absorb most, if not all, of the emissions, and not only the cars, but in fact the entire client's lifestyle. And all of this will only be about 9% of the client's property, so there's still plenty of land left for lifestyle and other uses if the client so desires. And this is a very economical solution which has a flexibility in the future when EV technology improves to then purchase EVs and upgrade the electrical system as well.
So for our final solution, our group has decided on design alternative 3, which, just to reiterate, was a hybrid system which was also grid connected, and additionally we would be planting trees across 10 to 16 of the 112 hectares on the property. This is just a system sketch showing how different components would interact. So this is the trees over here, where carbon offset was our main output, sunlight and wind were our main inputs, where they would be collected, stored, and distributed across the household. This system is connected to the grid as a backup, so that can also power the household when required, and any excess power can be sent back to the grid through feed-in tariffs. Also, we would have a home energy management system where it would collect usage data and make changes based on how much power is distributed and where across the system, or it can provide these analytics for the resident, and the resident can make these changes manually. So that's where we're at in terms of the system sketch and just the general design of the system.
Industrial ecology is a sustainability framework where resource utilization is optimized and is coupled with the minimization of waste through symbiotic interactions between varying components of a system. The social need for this framework applied in the context of our solution emerges as a necessity for transparency between the community and family as stakeholders. The constraint emerges as a difficulty in achieving widespread acceptance from said community. Industrial ecology poses an environmental need for maximizing resource efficiency while simultaneously minimizing waste production. However, a constraint emerges in the often significant waste and resource depletion of conventional industrial practices. Economic components of the industrial ecology require effective management of initial costs that accompany implementing sustainable technologies and infrastructure. This leads to the constraint of a high initial investment cost and dependency on economic cycles.